So let's look at the ends of a rational function, and I'm sort of going to assume that you've already watched my video about the ends of a polynomial function, because if you remember, the ends of a polynomial function behave like the leading term. Okay? That's because on the ends of a function, those are really big x values. We're talking about the left and right sides of the graph, so those are the big x values. Whenever the x values are big, the leading term dominates. All the smaller terms are insignificant. So this is also true for rational functions. So a couple examples. A rational function is simply a ratio of polynomials. So I might have 2x to the fourth minus 3x cubed plus x minus 5 over x squared plus 2x minus 7. And so if I want to look at the ends of this function, well, I know that this function on top 2x to the fourth is going to dominate, and on bottom x squared is going to dominate. So the ends of this function behave like y equals still the ratio, but now just the ratio of the leading terms and not the other insignificant stuff. And this ratio reduces. I can cancel the two x's on the bottom with two of the x's on the top to leave 2 on top. So the ends of this function behave like y equals 2x squared. And we know that 2x squared looks like this, so the ends of this function behave exactly the same way. Okay? So those are the ends of this rational function f. Alright, well, part of the problem now, though, is since you're going to have a ratio, a fraction, for your ends, you have to consider other possibilities. You know, we know x to an even power, both ends go up. And if you multiply that by a negative, it simply flips it over and both ends go down. Similarly, x to an odd power, the left end goes down and the right end goes up. Or if it's multiplied by a negative, you flip it over, the left end goes up and the right end goes down. But now you can have powers of x occur on the bottom. For example, you could have 1 over x to an even power. This is a little bit harder. Notice in x to an even power, sorry about that, in x to an even power, both ends are positive, meaning they go up. Well, this is 1 over x to an even power, so it's also positive. But both ends do not go up. In fact, both ends flatten out. So if this is your x-axis, the right end is positive, but it gets close to the x-axis instead of going up or down forever. And the left end is also positive, but it also approaches the x-axis. So the ends of the functions where you end up with more x's in the denominator, your graph is going to approach the x-axis on the ends. And you can imagine why, because if you look at big x values, and you have 1 over some big x value raised to a power, well, 1 divided by some really big number is really close to 0. And that's what's happening. As you get close to the x-axis, your y values are getting really close to 0. So you need to know, whenever you have 1 over x to an even power, your ends are going to behave like this. And you can probably imagine, if you have negative 1 over x to an even power as your ends, then you're still going to approach the x-axis, but from the negative side, because now it's flipped over and is negative. Okay? So you approach the x-axis, but from the bottom. And if you have 1 over x to an odd, the left end is negative, and the right end is positive. That's also true here. Okay? But you'll have to approach the x-axis. So here's our x-axis again. The left end is negative, but it approaches the x-axis. and the right end's positive, so it approaches the x-axis from the top. And if you multiply that by a negative, then you simply flip it over, and the left end approaches the x-axis from the top, and the right end approaches the x-axis from the bottom. Okay, so we have two more end behaviors that we did not have for polynomials, because we can actually end up with more x's in the bottom of a fraction than we do on top. You can also end up, when you look at the ratio, as we did over here, the x's could cancel out completely, meaning you get a constant. So, for example, your end behavior could be a constant, and a constant function always is a horizontal line at the constant. So, for example, if your end reduces down to 2, and then here's your x-axis, then you go up 2, and your ends are horizontal at the y value of 2. That's kind of hard to explain in general, so let's do an example where we see both of these and the constant. Okay? Alright, so f of x equals, let's do one where we end up with more x's on the bottom. So let's say we have x cubed minus x squared plus 5 over, negative 2x to the fourth plus 7. So for the ends, I know the top and bottom are dominated by the leading term, so my ends are going to be y equals x cubed over negative 2x to the fourth, and then I reduce, which is going to give me, let's pull the negative to the front, and actually let's pull the entire constant out so we can focus on the x's. So this will be the same thing as negative 1/2, because I'm pulling 2 out of the bottom, and that becomes a negative 1/2, and then my x's reduce to leave one x on bottom and no x's on top. Okay, so I get negative 1/2 times 1 over x. Well, this is a negative number times 1 over x. 1 over x approaches the x-axis from the negative side on the left and the positive side on the right. But because of the negative, I have to flip that over. So on the left, I'm going to approach the x-axis from the top, and on the right, I'm going to approach the x-axis from the bottom. So that's what the ends of this function look like. If I look at a ratio such as, let's look at another one, x cubed minus x squared plus 5 over now negative 2x cubed plus 7, my ends will be dominated on the top and the bottom by the first term, so y equals x cubed over negative 2x cubed, and that simply reduces to negative 1/2, the constant. So the ends of this graph, if I were to draw my coordinate plane, here's where y is negative 1/2. The ends of my graph would look like y equals negative 1/2, which is a horizontal line. But notice it's just the ends. I'm not connecting it all the way across the middle. So my graph behaves like this horizontal line on the extreme left and the extreme right. And there we have the ends whenever the ratio reduces to a constant. And those are all the cases for the ends of a rational function, with the main idea being that the top and bottom are dominated by their leading terms, and then you have to reduce the ratio to get the end behavior of the actual fraction, the actual function.